Welcome to more u-substitution examples. So for our first example, we want to find the integral of 4 cosine of 5x dx. Again, we're used to cosine. We're not so used to having something inside of that cosine. So this 5x will act as our u. So we're going to set u equal to 5x. Then du dx is simply equal to 5. And we get that du is 5 times dx. Solving for dx, we then get that dx is 1/5 du. This should look familiar to the previous problem we did in an earlier video. So the integral of 4 cosine of 5x dx is the same thing as the integral of 4 cosine of u times 1/5 du, or 4/5 times the integral of cosine of u du. Integral of cosine we know, that's just sine. So we have 4/5 sine of u plus c. And plugging back in, this is 4/5 times the sine of 5x plus c. Now let's go ahead and evaluate a definite integral. So we have the definite integral from 0 to 4 of the cube root of 7x minus 1. So we know how to evaluate an integral of a cubed root of x. That's just x to the 1/3. We know how to deal with the power rule. But here we have something inside. So we're going to set that 7x minus 1 is our u. Then we wind up getting that du is just 7 times dx. Or in other words, dx is 1/7 du. And so what we're working with is we have the definite integral from 0 to 4 of the cubed root of 7x minus 1 dx is the same thing as definite integral. I'm going to pause a moment before we put in the bounds, but we have the cubed root of u times 1/7 du. And then the bounds we're going to have to convert as well. So we have a choice here. You can either convert the bounds here, or we can convert them later. Or we can convert back to x and plug in. That's up to you. Personally, I would just convert the bounds here. So x equals 0 would mean that u is equal to 7 times 0 minus 1, otherwise known as -1. So our lower bound will be -1. X equals 4. Then we're working with u is equal to 7 times 4 minus 1. And that's 27. So our upper bound is 27. So since we've switched to working with du, might as well then also just work with our bounds in u. So at this point, again, this is the same thing as the definite integral from -1 to 27. I forgot to pull my 1/7 out front. So this is equal to 1/7 times the definite integral from -1 to 27 of the cubed root of u, otherwise known as u to the 1/3 du. The power rule says we should go up 1 and divide by our new power. So we are looking at 1/7 times u to the 4/3 divided by 4/3. And then we're evaluating from -1 to 27. Or 1/7 times 3/4 otherwise known as 3/28 of u to the 4/3. We're looking at the cubed root of u, and then that raised to the 4th, evaluated from -1 to 27. I need to give myself just a little more room. Plugging in, we have 3/28 times the cubed root of 27 raised to the 4th minus 3/28 times the cubed root of -1 raised to the 4th. So this becomes 3/28 times 81. Cube root of 27 is 3 raised to the 4th is 81. And we have minus 3/28 times cube root of -1 is -1 raised to the 4th is just 1. So this is 81 minus 1, or 80 times 3/28. Or if we divide by 4, that's 20 times 3/7, or 60/7. So assuming I did not make a little arithmetic error at the end, this is our definite integral. Let's go ahead and do one more. So if we want to evaluate the definite integral from 0 to 1 of e to the x squared minus 1 times x dx, we'll go ahead and here's our composition. So we'll set u equal to x squared minus 1. Then we have du is equal to 2x times dx. Note that we have x dx remaining. So we will solve for x dx, or you can just solve for dx and cancel things out then later. But since we do have an x dx, we might as well just solve for that. And so we have that x times dx is just equal to 1/2 du. So we have our definite integral from 0 to 1 of e to the u times 1/2 du. And the thing I underlined in purple is just that piece there. Except my integration, oh, sorry, I was actually going to write this first in x and then in u. Let me do that. The integral from 0 to 1 of e to the x squared minus 1 times x dx is equal to the integral from something to something of e to the u times 1/2 du. Again, I'm taking my x dx and replacing it with 1/2 du. For my bounds, here x equals 0. We're going to convert using u is equal to x squared minus 1. So u is 0 squared minus 1, otherwise known as -1. For our upper bound, we have x equals 1. And so we have that u is equal to 1 squared minus 1, otherwise known as 0. So we're now integrating from -1 to 0 instead of from 0 to 1, since we're now working in u instead of x. So this becomes then, we have 1/2 times the definite integral from -1 to 0 of e to the u du. Integral of e to the u is just e to the u. So we have 1/2 times e to the u, evaluated from -1 to 0. This becomes 1/2 times e to the 0th minus 1/2 times e to the -1, e to the 0th is just 1, so we just have 1/2 minus, and then e to the -1 is 1 over e, so we have 1 minus 2 over e. That way, you could also write this as 1/2 times 1 minus 1 over e if you didn't want to multiply in 1/2 till the end. I did make a comment that it is possible to do these products without changing bounds. You just have to convert back to x at the end. So just a note, if you do not want to change the bounds, then we can convert back to x before you plug in. So again, essentially what we could have done is we had the definite integral from 0 to 1 of e to the x squared minus 1 times x dx. Okay. What we could do is we could focus on, we could find an antiderivative. So we will look at the integral of e to the x squared minus 1 times x dx. And we could have used u-substitution. Again, with u equaling x squared minus 1, we have du is 2x times dx. We get that x times dx equals to 1/2 du. So we can go ahead then and convert. So we have the integral from e to the x squared minus 1 times x dx. That's the same thing as looking at the integral of e to the u times 1/2 du. If we integrate this, this becomes 1/2 e to the u plus c, or 1/2 e to the x squared minus 1 plus c for our antiderivative. So going back then, the definite integral from 0 to 1 of e to the x squared minus 1 times x dx is the same thing as 1/2 e to the x squared minus 1 evaluated from 0 to 1. And we'd have 1/2 e to the 1 squared minus 1, subtracting 1/2 e to the 0 squared minus 1. And we have 1/2 e to the 0th minus 1/2 e to the -1. It should look familiar. And we wind up with 1/2 minus 1/2 times 1 over e. Right. So we get the same result as we had before. This is just two different approaches. So you can either think of it as just finding the antiderivative, get it back in terms of x, and then evaluate your definite integral, or you can convert the bounds to u as well and evaluate the definite integral that way. So either approach works, but this is how we go about doing u-substitution.